Okay, so this is the second video in phase 5, and it's about how I use the step instruction to troubleshoot. The reason why you would use something like this is because it breaks the code down into various sections, and we'll demonstrate how we do it in a second. And I've got a little sort of presentation slide that I can show. So the first thing to do is step one within writing any piece of code is to understand what you're trying to do. So with our with our code here, we've got CLCs, which we've demonstrated before, so we know that clears the carry. We've got the LDA immediate, which again we've demonstrated before. We know what that's meant to do. It's meant to put AA into the accumulator. Then we've got this instruction, which is ROR. And ROR says rotate 1 bit right. Okay, and that's either for memory or accumulator. Now we've got 6A in here, so 6A is based on the accumulator, and we know it's 1 byte long because we can see it there, and the disassembler has disassembled it perfectly, so it's 1 byte long. It's therefore acting on the accumulator. Then we got this lovely command here, and you kind of got to think, well, okay, so what is a BPL? What does it do? Well, BPL is one of the branch instructions. And you have to, there are several of them, and they kind of use the various flags. We've insinuated that before. I'm going to find it. It's up here somewhere. So the BPL. Okay, so BVS, BVCs. These are all the different branch instructions to break, isn't there's BPL. Branch on the result being plus. The result of what? Well, the result of the last instruction is the answer. So it checks the status register, and what it basically says, and it tells you, it says it there, branch on the negative flag being a 0. Right? It doesn't affect any of the flags. All it does is it says, is the negative flag a 0? If the answer is yes, take the branch. Now, what this branch says is branch FF, and that is a negative number, and what that represents is -1. So in this case it says branch -1 from the position that I am, and I'm going to go back to here and do this rotate again, and then I'm going to check again, and then I'm going to branch again, and I'm going to check again, and up until the point where that number in the accumulator is positive, because we know it's positive because that ROR, as before, we saw it further down, it said, ROR said it does set these flags. It said it set the N, the Z and the C flag. Now we can demonstrate that, but before we do, I'd like to demonstrate it on a slideshow. Okay, so this is our slideshow, and what it does, if we it starts off by, when we say go, we load the program counter, that is, with the address of C20F, because that's the start of our code. And the start of the code, the first thing it does is it then says, I'm going to execute the first instruction, and the first instruction is clear carry, and that sets the carry to 0. Irrespective of whether the carry was 0 before, it sets it to 0. Then it increments the program counter once more to point to the next instruction. And the next instruction is a load of the accumulator with the value of AA. And the value of AA has a high bit of 1, and that high bit of 1 sets the negative flag. Then it increments the program counter, points it to the next instruction. The next instruction is a rotate right. Now the rotate right has a couple of phases. It does, for the sake of demonstration anyway, it kind of does it quite quickly in the 6502, but for our demonstration, in a way, and it kind of highlights the way we've done it, or the way I've done it in the emulator. And what it does is it saves the current carry bit into a temporary location. The 6502 doesn't. The 6502 does this a lot quicker, but we're doing it this way. And we also take bit 0 or bit 1, if you like, and store that into a temporary location. Then phase 2 takes the contents of the accumulator and moves it right 1. So you can see that all the ones are moved right one place. and then it moves the previous carry into this location, and it moves what we had in bit 0 or bit 1, it depends on how you describe it. I tend to describe it as bit 0, but it's the first place here, the ones place anyway, and pops it into the carry. And then it also sets the negative flag based on the high bit, so you notice there that that bit is now 0. Then it increments the program counter again. Then it says, let's have a look at the branch. Now the branch on plus, we saw that if the negative flag is 0, take the branch. It does. And because it takes the branch, it basically adds -1 to the program counter, and that's how it does it in the 6502 as well. And it puts it back here. So we end up doing the roll again. So we rotate right. So the first thing it does is it copies our bit 1 into there, the previous carry into here, and then shunts them about. So now the carry is a 1, the high bit is a 0, and the negative is a 0. Increment the program counter, check the negative flag, perform the branch. Okay. Now do the same thing again. Move these into the temporary locations. Move them in. Now notice at this point the high bit is a 1, therefore the negative flag is a 1. Okay, doesn't mean our number is negative. It means that the machine sees it as potentially negative because this high bit is 1. Increment it. Test the bit. Negative bit is not a 0. Don't take the branch. Therefore, move on to the next instruction, and it will continue with the program code sequence at that point. So that's how. That's what we would expect to see given that set of instructions. So the question is that what we see? Well, this is where the step instruction comes in really nicely, because if we say step to C2 0F, we can see that the step instruction now also displays the registers at the end of each and every step, which is quite useful to us. So the first thing that it does, and you have to remember the step instruction is slightly out of sequence to where you would I'll explain that as we go along. So the first thing it's done is that clear carry. There we go, clear carry. Carry is clear. Okay. In fact, before we start that again, let's toggle that. Let's toggle the carry, and you can see that the carry is now a 1. And now if we step from C20F, first thing it does is clear the carry. All right. Now if we step again, what was the next thing we expected it to do? Load AA into the accumulator. Does it do that? Yes, it does. I'll tell you what we'll do. Oops, we'll bring it up here. There we are. Because now we can see what's going on. The next thing we would expect it to do is a rotate right. So it's popped the AA into the accumulator, and it has set the negative bit to 1 as we would expect. So now we step again. It's rotated. We've got that 5 in there. The zeros in the carriers was in the presentation slide. Negative flag has been flipped to 0 because the high bit on 5 is a 0. Step again. Now it goes and does the branch. Notice the program counter has moved from 213 to 212, which is exactly what we would expect it to do. 213 is here, 212 is there. It's taken the branch because the negative flag is 0. So we step again, and it rotates again, and we got that 2A, which is what we would have expected to see. We saw that on the PowerPoint slide. The carry is 1 still. The carry is now 1 because it's moved the 1 out of the low bit into the carry, and that's correct. We step again, and it checks the branch. Does it take the branch? Yes, it does. So it's taken the branch again, and that's perfectly legitimate because this negative flag is 0. So we go back through the ROR again, and this time it's rotated it, and we've got 9.5. Now this time the negative flag is 0. So what we should now expect to see on the branch, Our program counter is 213. This is 213. The next instruction we're going to be running is the branch, and it's going to say I don't think so, and it should end up with the program counter pointing at 215. And there you go. So the program counter now points to 215 because the branch failed because the negative flag is set. So that branch on plus is a tested functional instruction, and that works exactly as we would have expected it to. So how is this useful inside of debug if you're going to test your instruction set? Well, because we've already proven that the addressing modes work, we did that in the previous phases. We don't need to test those. These are working, and that is fine. So therefore 6A takes the memory pointer and points it at the CPU accumulator. So in reality then it's only this down here that needs to be tested. Now if you remember our process that we put into play, this is effectively what we're doing. We're copying our previous carry, so our current status register carry flag, into a temporary variable, and that's SR ANDed with 1. If you remember one of the earlier videos, we talked about how the AND works, and that basically says if the rightmost bit is 1, then that becomes a 1. If the rightmost bit is 0, because AND has to be both to set the bit, then that becomes a 0. So therefore it will copy the contents of the status register carry flag into the carry. Now what this bit does is this bit's one of those if statements that you can use in C. So what you have is you've got the condition on the left hand side here, something to do if that condition is true, and something to do if that condition is false. So that's what this question mark and colon mean. I think they call it a ternary if or something. Anyway, so what that says is take the contents of the memory pointer, which is effectively the contents of the accumulator, because the memory pointer is pointing at the accumulator. And if you remember our demonstration on pointers, what that is pointing to is the same thing as what is in the CPU underscore A in for our accumulator. It ANDs it with 1, and it says if it's true, set the status register to 1 by using that OR command, and if it's not, clear it. So what that's doing is the second step of that. So it's saying first of all we've copied the original carry flag. Now we're setting the status register carry flag based upon what was in the rightmost bit of our accumulator. So that's done, nice. Now what we're going to do is shift, and remember that again is there, so that shifts, right shifts by 1. Now this takes our temporary carry flag, shifts it right by 7, so it moves that 7 bits right into the 8th position, and ORs it with what's in here. So therefore it sets that bit. Okay, so it sets that bit to whatever the previous carry was. So if the carry was 0, it will set it to 0. If it was 1, it will set it to 1. Okay, and whatever's in the and because we know that it's a 0 in there because we've shifted it, it works well, and you've seen that demonstrated. Then it tests it. It does the usual tests to say, do I have to set or clear the negative bit, and do I have to set or clear the negative flag? And that's correct, because if we go back down to the ROR, which was down here a goodly way, I wish I'd have set this up before the video started, but anyway, never mind. There we go. If we have a look at our ROR, that is absolutely spot on, because they're the 3 flags it sets, and within our code they are the 3 flags it sets. So we've already set the carry flag, because the carry flag was set at this point here. Now we're setting the last 2 flags, which is the negative flag and the 0 flag, based upon that instruction. So we've followed our own process. We've understood what the instruction does. We've written code to deal with it. We've tested the instruction. We've fixed any errors that we've found, and then we've retested. Okay, and that same process was applied for all of the commands, irrespective of what it was. I wrote a series of code within here to deal with everything. It's not all there now, of course, but each one of these, I know I've tested things like not only the BPL, but I've tested branch on negative, branch on overflow, and for a lot of these, because it was easier to do, I actually used the toggle command. So I use the T command to things like set the overflow flag there, like that. So that would allow me to test the BV commands, branch and overflow. So branch and overflow set, branch and overflow clear. They could be tested in exactly the same way. And if we go on to the branches, you can see that they're all here. Look. So each and every one of these was tested, but most of them were tested with the toggle command. And in some cases, I just typed in the op codes and the operands into the emulator manually using the insert feature, which we've used a long time ago in a previous thing before I wrote the memory. Before I used the memory initializer, you know, the mem function there, the memory file there, we used to use the input command, and the input command allows us to type in, so it's insert command rather, insert memory address and then the value. So, you know, we could put in specific code to test whether or not it takes the branch or whether it doesn't take the branch. But the same process is applied, is understand what the instruction does by go looking it up in here, write a bit of code to deal with it, test that bit of code in here, fix any errors, go back and test, fix the errors, go back and test, and this entire cyclic loop only gets broken when that code is fixed and working. So this process was done, or it has been done, for quite a lot of these instructions. The only ones I'm not fully happy with at the moment are the add and subtract, because they've got some weird overflow stuff, but I'm in the process of fully testing them at this moment in time. But everything else I think is pretty much working. Might be the odd bug here and there, but I think it's other than that, it's spot on. So that's how I use the step command to do this.